speaker today is Professor Ashok Kumar Ganguly. He is at the Department of Chemistry in IIT Delhi. He got his PhD in the solid state in the IIT Bangalore in 1990 in the area of thallium-based high-temperature superconductors, for which he got the Sudbury Medal. He's been a visiting scientist at DuPont and a postdoctoral associate and visiting scientist at Ames, Iowa State University. His interests are in the synthesis and properties of materials such as dielectric and superconducting oxides, quaternary chalcogenides, polar intermetallics. Oh, I'd like to find out what that is. I studied chemistry at the beginning of my career. And nanocrystalline materials.
Very glad to be here, and I was called by Prem Kalra of IIT Delhi, and I couldn't refuse him, very good friend of mine. So I'm here today to talk to you on some material aspects towards nanotechnology, and try to give you some idea about how it can be used towards nanocomputing, because this meeting is on quantum computing and nanocomputing. So, what I thought I will do is I'll give a brief introduction to the general ideas of nanowires and molecular devices and some aspects of molecular electronics and what kind of molecules or materials are required for these kind of devices, and especially show you how you can synthesize these nanowires, and then come to one method which is used for making these nanowires using microemulsions, because that's the area I work these days to synthesize and control the size and shape of nanowires and nanorods. Of course, I also work on quantum dots, so I'll just discuss these synthetic approaches. Before I start, I just want to mention that regarding that comment on last question regarding the human brain and the computer, what I understand is that the human brain is a very dynamic network of neurons, and that's very different from the machine networking. And the human brain is always learns according to situations, and that's something which is very difficult to replicate, and that is where artificial intelligence has to work upon, how to dynamically change the networking. And to make the ultimate computer, of course, there is not like the brain, it probably has to come from biomolecules, and it has to grow in solution. As you know, life was created in the sea, and there was a very good lecture by Nobel laureate Jean-Marie Lehn. I heard him 2-3 times, where he is now working on these ideas that if you have to build an ultimate intelligent system, it has to have, it will come out of a flux of molecules in dynamic equilibrium and in a soup, so like in the sea, and from that you will generate the ultimate machine. But these are many big ideas which are floating around. So just to tell you, as we are going from microelectronics to nanoelectronics, what's happening is that you are now having to deal with systems which are few nanometers in dimension. I'm sure in this meeting a lot has been discussed earlier on what exactly is a nanoparticle or a nanorod, so I won't go into all that. What kind of physical properties like optical properties or the band gaps, how they vary. Just to tell you that in a typical PCB, you see these kind of array of components which have the separation between the minimum features are of the order of worse of the order of few micron. Today, I think the smallest difference between two features is around 140 nanometers. And these molecules, of course, as you know, are much, much smaller. So the goal is to make the feature size smaller and the difference between the features to be smaller. That is called the pitch between two, say, transistors or something like that. Now, this is a carbon nanotube, and the carbon nanotube has been connected by a molecule which has some antenna-like features to harvest light. This is just a picture to show you. This can do some jobs it can do, and this dimension is around 30 nanometers. So this is the kind of dimensions today people are talking about to build molecular systems for electronic applications. And this, of course, all of you know, the famous Moore's law, which shows that we are having difficulty in touching the pace at which Moore's law is supposed to go up. So these are the no solutions. The red ones are we don't have solutions, and the yellow ones where some solutions are being attempted right now. So the solutions which are being attempted, say in 2010, are much below what is expected to touch the Moore's law. So we are lagging far behind what is expected. Now, what I want to say is that in nanoelectronics or molecular electronics, the molecules are very important. So you have to understand how to make the molecules and how to assemble the molecules. Making molecules is one thing, and then assembling them is another thing. Now, this is a typical way how physicists, applied physicists, and engineers work to make structures, and this is called the top-down approach, where you use lithography. And this is the standard approach, one of the standard approaches by which you make nanostructures. So you start with a glass substrate, you have a indium tin oxide on top, this is a polymer, and then you use an electron beam to make patterns, and then you can lift them off ultimately. You put gold and then you can lift off the gold. But this is not the approach that molecular electronics is taking today. The other approach which is important is the bottom-up approach. That is, you start building with molecules and you network with molecules. This is a schematic to show you have these quantum wires or nanowires, and you have these organic molecules which are going to connect these wires. So you can make kind of a transistor out of this, and based on the electronic transport through these organic systems. Now, the most well-studied molecular system today is the carbon nanotube. And the carbon nanotube, as you know, is made up of carbon, and these carbons are arranged in either hexagonal rings or pentagonal rings. It is hexagonal in the linear part, whereas it becomes pentagons at the region where the tube curves. And there are different types of tubes depending on certain patterns. I won't go into that. And depending on the patterns, these tubes can be semiconducting or metallic. Okay? And you can have different types of these carbon nanotubes. And these have been used over last 10 years. As you can see that 1998, the first single nanotube transistor was made at IBM, and then field effect transistors were made. The smallest computer logic circuit was made in 2001. So several things have happened, and this is a schematic to show how a carbon nanotube is being used to make an interconnect. Okay. Now, just without going into the networking, just if you take nanowires, nanowires itself have a lot of applications. Okay. One of the applications is it can be used as, if it's an N-type, you can make it N-type or P-type nanowire. It can be used as a transistor, and the mobility of the electrons or holes is much higher in these silicon nanowires. And this has been gone through a lot of work. Silicon nanowires have been studied a lot. And other than in electronics, it has lot of role as a sensor. It's a biosensor. And there is lot of work on silicon nanowires, how you put on the nanowires some antibodies and you can detect viruses and other pathogens, etc. The conductance of the wire, what you do is you measure the conductance of the wire with the pathogen, without the pathogen, and that gives you a signal. It tells you, and this pathogen is very specific. So you have some antibodies on the nanowire, it will bind to a specific pathogen, and so it is very selective. So it is a very good biosensor. So these nanowires or quantum wires are very good biosensors apart from their use in electronics. So this is another example. I just want to show you that it has been used, silicon nanowires has been used to detect proteins, DNA, lots of things. I won't go into that, just to give you an example. What I want to show you is in electronics, people have already made different types of nanowires. This is silicon nanowires, and it has been grown by the standard. This is a very standard technique of growth of long crystals. So earlier people used to make large crystals of silicon to make single crystalline silicon wafers, and nowadays people are using the same technique to make thin wires. Instead of making large crystals, have the diameter very small but very long wires. And these are TEM pictures to show that the wire is very uniform by this method. You can see at one end it is 33 nanometer, and I think on the other end it is 32 nanometer. So you can precisely control the diameter of the nanowire by this standard vapor liquid solid method. And this is a very old paper which gives the mechanism of this growth of wires, or you can grow cylinders if you want of single crystalline silicon, where you have a substrate, silicon substrate, and then you have a gold silicon liquid alloy, and then it is grown slowly. So there is a vapor on top, right? So there is a vapor, there is a liquid, and there is a solid. So that is why it's called a VLS method. And this paper is in 1979, Applied Physics Letters, where it was shown, the mechanism of the VLS method was shown. So the same method is being used now. So instead of making large crystals, which was the aim those days, today's aim is to make very thin fibers of the similar materials. Now this is more recent. This is the work of James Heath at Caltech, I think, and this is the modern technique of making nanostructures, where the technique is called the superlattice nanowire pattern transfer technique. And in this example, what is shown is you have a gallium arsenide substrate, and on that gallium arsenide substrate you have some aluminum gallium arsenide semiconductor, and then you etch it. You etch it in such a way that part of it goes away, so the top part is exposed, and then you can remove that gallium arsenide by some chemical methods, and after that you basically can transfer it, you can on a silicon substrate. Okay, so basically what you are doing is you are making a lattice, you are designing a lattice, and you are transferring it on a substrate. That's why it's called a superlattice nanowire pattern transfer. So these wires has been now transferred onto the silicon wafer, which was at the bottom. Okay, in between there is a epoxy resin which can be burnt away. So this methodology is very popular today to make fine wires of metal or silicon by which you can make interconnects. So this is a SEM picture to show you these are platinum wires made using this technique by the snap process, and can be used for devices. So you have got very fine wires of around 20 nanometers in dimension, and these are very well patterned with very uniform distances in between. So this is a real picture of that. That had only 9 wires. Now you have several wires. So this small area is like 0.1 microns, and if you blow this up, you will have a very regular array of nanowires, and the challenge is to reduce this distance between the wires. So you have to reduce the diameter of the wires, and also you want to reduce the distance between the wires, which is called the pitch. And you can see here it is around 60 nanometers, and you can generate 16 nanometer in silicon. So a lot of work has been done by James Heath in Caltech on aligned platinum silicon nanowire assemblies. This is a real device made by these nanowires. So this is basically a very small, it's a molecular switch, and what you have here is you have 2 electrodes. The bottom electrode, this red part, is made up of these silicon nanowires. So you have silicon nanowires, the ones I showed in the previous slide, patterned. So there are around 400 silicon nanowires in this region, and this is of the size of one blood cell. So you can imagine how small it is. It is the size of one white blood cell, around 13 microns, and it has got 400 silicon nanowires. The top electrode is going like this, and that has got 400 titanium nanowires, which is covered by platinum. So the titanium wires are covered by platinum, and it has been grown by the same snap method, right? So you have 2 electrodes, and now the molecule comes into picture. The 2 electrodes, in between the 2 electrodes, you have to put some molecules which will talk to the 2 electrodes. So those molecules are basically a class of molecules called rotazane. I'll just show you what is a rotazane. Okay? These are molecules which change their orientation under external stimuli. That means you give some kind of current or something. So basically what it does is you have 2 electrodes, and there are these molecules in between them. So one part of the molecule is attached to the top electrode, and one part of the molecule to the bottom electrode, and you pass electrons through them, and it acts as a switch. And this is, one of these is 1 bit, and they have been able to make a 160 kilobit device. And in these devices, the distance between the wires is 33 nanometers. By conventional lithography, to achieve this, is predicted that you will achieve this in 2020. So this is a great jump in technology by the solution or molecular method. Okay? So this is a rotazane molecule. It's not very easy. It's very complex, means to make these molecules and put it between the electrodes. So this lot of work. So this is a rotazane molecule. So the top, I showed you 2 electrodes. The top part is the platinum titanium nanowires, that electrode going linear. So one part of the molecule is designed that it will tether itself to the top part. So there is something what we call, there is a hydrophobic end. Okay, in chemistry, hydrophobic means something which does not like water. So it doesn't like polarity. Okay, and the other part is hydrophilic. It likes silicon. Okay, so the hydrophilic part likes silicon, and the hydrophobic part likes titanium. That's how you design it, and this molecule then fixes itself like this. Now, what happens is when you pass a current, that is when an electron goes in, this is the mechanism, and this is a slightly different molecule related to this. This is a linear molecule, This you can see it's not linear, but it has similar features. You see there are these blue ones. This is called a cyclophane, if there is any chemist here. This is called a cyclophane molecule. And this cyclophane molecule you can see here, the black ones. And the linear part here you see is actually also circular. So it's like two rings, one going between the other. When you pass an electron, what happens is that there is this, what we call a TTF molecule is embedded. You see this 4 sulfur atoms, it's called tetrathiophenylene, okay, TTF molecule. This TTF molecule gets charged, okay, when you pass an electron. The moment it gets charged, you have you take out an electron. Here you are minus electron, so it becomes positive at one end. When it becomes positive, the other molecule has positive charges. You see 4 positive charges. So it doesn't like that positive charge. So it pushes this molecule out. So what happens, there is what we call a circum rotation. The molecule rotates by itself because of electron transfer. So this is like an actuator. Okay. So the molecule rotates and this part comes out. Now it was inside, it has come out. Okay. So here what it does in this device, because it is not circular, what happens, this part, when it loses an electron, it becomes positive, it repels this part, the blue part, and the blue part translates and comes down here. So it moves here after it loses an electron. When it gains an electron, that part from here it will go back there. So it will go this movement of up and down when electron comes in and goes out. So based on this is called a bistable rotaxane, which is used as a switch under redox conditions. That means when you pass electron or you take out electron, and so it can act as a molecular switch. So the chemistry was done in 2000 in this system, and they took the idea. In 2007 they made this device. It's published in Nature in 2007. Now this is another system which a lot of people are working. DNA has now become very cheap. Any lab in India can also make DNA very easily. And DNA has a lot of interesting things because in DNA, as you know, DNA is deoxyribose nucleic acid. It's part of our human body. It has got certain kind of addresses which can be recognized. Okay, so there is something called complementarity in DNA strands, which device people are making use of it. Okay, so let me tell you what Tom Maluk at Penn State does. Okay, he is also a very good molecular chemist working in molecular electronics. You want to bring in wires together, because ultimately in a device you have to have a lot of networking. So how do you bring wires together which are of the size of nanometer dimensions? So one way is you have these metallic wires. This metallic wire, suppose this is any platinum wire or titanium wire, part of it you add gold, because gold has a interesting ability to bind to DNA. So you coat gold and use a DNA with a thiol unit. SH group is called a thiol, like an alcohol has a OH group in chemistry. So this sulfur of the thiol group will bind to the gold. So what you have done is you have brought one DNA molecule on top of the gold surface. Then what you do is you have other rods or other nanowires which has the complementary part of the DNA. When you do that, the other wire will come close and bind, and it will form a double helix. You see, this is a single strand DNA, and when it binds, this lower one binds to the top wire through the DNA molecules, and the single stranded DNA now become double stranded DNA because they are complementary, so they bind. So this is one way of bringing nanowires together using DNA as a mediating agent. So, because DNA has this complementarity and DNA can be thiolized and hence it can be attached to gold wires. So, this technique is also very popular. Now, if you want to assemble wires like you want to have 90-degree network, one layer in one direction and you want to make a pattern above another, then you can use another technique which Charles Lieber at Harvard has done. You have a typical PDMS, it is a polymer, very standard polymer with device people, and you make channels in them. That means already you make some channels using some method in a the pattern should be the way you want to design it basically. So, once you make those channels, now you put a solution having all your nanowires. Now, there will be millions of nanowires, they are all in different directions. So, how do you orient them? So, what he uses is he passes a flux of fluid and this fluid is ethanol. So, when the fluid flows, it aligns the nanowires into the channels. So, you get an array of nanowires in the grooves which was already made in the PDMS mold. Okay? And then you put another PDMS mold on top of it and flow the liquid perpendicular to it. So, now the nanowires will form a 90-degree intersection with the previous. So, that is how now you have a pattern and you have a lot of points which are connecting. So, you have now a lot of metal wires intersecting each other. Now, this is a technique by which you use a template to make a wire which can be conducting. So, you start with a template. The template can be a carbon nanotube. That is the simplest template you can choose. So, you have this carbon nanotube and then you do the chemistry on the carbon nanotube. So, what you do is you add all these liquids. They have got a metal source, platinum, you can read here PT. This is a solution called chloroplatinic acid, okay? And you add some formic acid and water, and what you start getting is platinum particles on top of the carbon nanotubes. And as you continue the reaction, you can study it under a high resolution transmission electron microscope. The particles will grow. So, this is a bare carbon nanotube, and as reaction is proceeding, you are having small particles of platinum deposited on the carbon nanotube, and with due course of time they will form oriented growth. So, this is the carbon nanotube, and on top of that you will see these agglomeration of or assembly of platinum particles growing as rods. Okay? So, this is another way you can generate nanostructures which can be used for interconnects. Then you can, this is the SEM or TEM picture of that carbon nanotube you can see here, and the platinum nanowires growing on top. So, depending, because platinum will be much more conducting, so you have a junction, because carbon nanotube you can choose a semiconducting carbon nanotube. So, you can use it in devices as junctions, as a metal insulator junction or metal semiconductor junction. These are more high resolution pictures. If you increase the concentration of your solution, there are many controls. You can modify them, how much amount of chloroplatinic acid are you taking, etc., by which you can generate slightly more different kind of features on the carbon nanotube. So, here these features you get when you use much larger concentration of chloroplatinic acid. Now, coming to the area of my interest is nanowire formation in microemulsions. So, I will just tell you what is microemulsion a little later. Basically, you can see that there are some hair-like structures. These hair-like structures are nothing but these are some carbon fibers, long chain carbon fibers, and these carbon fibers at their end have some kind of a charge, we call it a polar head, and they form lots of different structures. They can be spherical, they can be lamellar, they can be worm-like. These are called worm-like micelles. Okay? I don't know whether some worm-like here. So it depends on the concentration of different chemicals that you have taken. To make one particular solution of a microemulsion, you need 3-4 components. Okay? You may need alcohol, you may need alkane and some water, and the thermodynamics will make the molecules align in a particular fashion because it has to reduce its energy, right? So depending on the nature of the initial molecules that you take, you will get different types of structures. In this case, it's like a worm-like micelle. It is kind of not allowing the particles to grow freely. It is channelizing them in a particular fashion. So all the platinum is growing along a particular direction, and it forms this kind of Y junctions. In today's world, these are called Y junctions. Okay? But you can get linear nanowires or many other things. So this aspect, now I will discuss further, that using microemulsions, what all things you can do. So I will go into detail in these kind of things. This is just an X-ray to show those are platinum. This is a SEM picture of those platinum nanowires. Okay. So let me come to microemulsions, which is what is a microemulsion and how you grow particles. The aim in nanoparticle synthesis or nanowire synthesis is you should not allow the particle to grow or aggregate. Then it will become a micron sized particle, right? Then, so you have to restrict the growth of the particle. And to restrict the growth of the particle, one of the best methods is the microemulsion method, which I just gave you an example. So what is a microemulsion? If you take any two liquids which are immiscible, like oil and water, they will not mix. But then you add some surface active agent, in chemistry we call, or in chemical engineering, and this surface active agent job is to reduce the interfacial energy between the non-aqueous medium and the aqueous medium. If you shake two liquids which are immiscible, they become miscible for some small time till you give the energy. That is, by mechanically you can stir them and make them homogeneous, and they will form droplets which you will not be able to see by the naked eye. Okay? So these droplets you can't see with your naked eye, only under some kind of a freeze microscopy or something you can freeze these things and see, but you can't see them. So this transparent, it becomes transparent, but it will not remain transparent the moment you remove the energy, right? But if you use a surfactant, which is a chemical substance which provides that energy or which lowers the interfacial energy, so you don't need to provide that energy, you will get these kind of spherical things, and actually they will be much smaller, and so it will be transparent and it will be stable since they are very small. So it will not come back to this mixture in the presence of the surfactant. So that's the whole game of microemulsions. That is, you try to make structures in a solution. So you have, in this case we are making spherical structures, but with proper choice of surfactants you can make lamellar structures also inside the liquid. So once you make these structures, they act as templates. After that reactions if you do, then the molecules or particles which will form will take the shape of the template which you have generated in solution. Okay? So microemulsions basically give you a template to prepare particles of designated shape and of size if you can control the size. So the size of this normally is in the nanometer dimension, and hence you get nanoparticles. Okay? But how much nanometers, whether it is 5 nanometers or 3 nanometers or 40 nanometers, that depends on several your choice of reactants, etc. So this is a closer view of what happens. There are these surfactants which I said are chemically active molecules which you use in your daily life, as soap is a surfactant. which has a structure which has a long chain and a slightly larger head, and this has a charge normally, but it can be uncharged also, and they have different interests. This likes to be move with water, this does not like to move with water. Okay? So, they have different behavior. So, what happens is this molecule is always at the interface, because half of it is in water, half of it is outside water. So, it likes to be at the interface, and that is why it lowers the interfacial tension of the liquids. So, what we do when we synthesize nanoparticles or nanomaterials or nanostructures, we make these kind of microemulsions, and these microemulsions, 2, 3, 4 microemulsions we take and we mix them, and one microemulsion will have some ion inside, say platinum, and I want to make it into, say, platinum oxide. So, I will have something here which will turn it into an oxide. So, I mix them A plus B and get the product. So, normally if you do not use microemulsions, also you can do this reaction, but you will get large size particles. So, you will get micron size. Normal particles you will get is micron size. But if you use microemulsions, you will get same particles, but restrained to the size of the structure which you have created in solution. And so, you will get small sized objects, and this is a way of control of the size of these particles. Okay? So, other than spherical structures, as I said, this is what is the most popular structure which is used, which is spherical, and it is called a reverse Micelle, because this is pointing inside. If it points outside, it is called a Micelle. This is just a terminology, but you must know that when it points inside, since it likes water, water has to be inside, water cannot be outside. If it points outside, then water has to be outside, and no water can go inside, only oil can go inside. So, that restricts the kind of synthesis that you will do by designing this. You can have very complicated things. Some of these are in our human body. Human body has vesicles, etc. It has got bilayers. These are called bilayers. You must have heard of lipid bilayers. All transport of ions, etc. inside of body is controlled through these bilayers. Okay. So, you can make products based on this. Now, there are a lot of what kind of surfactant should I choose. So, based on the length of the carbon chain and the head group, etc., you can design what kind of micelle you want, right, and take a suitable molecule which has a particular area or particular volume of the head group and particular length. So, you can do some minor calculations and choose the type of surfactant molecule, etc. So, this is to show how the molecules, the surfactant molecules will be sticking out from the oil, and this process is entropy driven. Basically, it brings a disorder in the solution. So, it brings a disorder means more entropy, reduces the energy of the system. So, the process goes forward. Okay. These are some of the chemicals which are used. I don't know, it's too much chemistry probably, right. These are the normally the acronyms which are used for these, and these are the formulae, and they can be anionic, cationic, non-ionic. There can be zwitterionic, means it can have two charges, plus minus both in the same molecule. So, if you keep adding these surfactants, if you add less surfactant, they hang on to the surface. Beyond a certain concentration, they start reorganizing among themselves, okay, and they form spherical micelles. So, this particular number which you reach, after which it becomes like this, is called a critical micellar concentration, which is a very important parameter when you do synthesis. And you have to know that you have several parameters now. Oil is there, surfactant is there, water is there. Sometimes we have a fourth parameter which is called a co-surfactant, and you must know when you have to plot what is called a phase diagram. That means if I take X amount of this or Y amount of this or Z amount of this, what will I get? So, by knowing the phase diagram, you know what kind of structure you will get. Okay? So, you can get a micelle or a reverse micelle or a bicontinuous medium, etc. So these are all design. So these are some materials, nanoparticles we make. Okay, I missed that. Okay, this is just to show we make dielectric nanoparticles, we make rods of different types, and we make magnetic oxides. These are more two particles within each, two nanoparticles, one inside the other. These are bimetallic alloy or metal nanoparticles or nanorods. Okay. So a lot of things we can do. And what are the parameters that we study to control the size and shape? Because our main aim is to control the size and shape of these nanostructures. So you can control the solvent, the surfactant, the amount of water you add to the surfactant, because it will control the size of those. We call them nano reactors, because the reaction is taking place in those small volumes of those the structures made by the surfactants, and several other things. So this is a typical case of making rods of some metal carboxylates. So we have a microemulsion based on a cationic surfactant, and these rods are aligned because the surface of this rod, because of these oxygens, becomes negatively charged, and these cation surfactants have a positively charged head group which blocks the growth of the rod in this direction. So there is a tendency to form or grow in only one direction. Okay. So you see these rods which have diameter of around 60-70 nanometers, but they are very long. These are TM pictures. Note that if you don't use microemulsions, if you use a standard chemical route, then you will not get these rods, you will get only particles. Okay. So using these rods, of course, you can make more interesting oxides, because oxides are more important for making semiconductors or magnetic materials, which will be used for devices. Now, one of the aim of our aim is to control the aspect ratio of the rods, because you need to control the length and the width of the rods. So if you want to make rods or wires, you have to control them. And we have done a investigation, detailed investigation, how you can control this aspect ratio by varying the kind of solvent. This is to show if you change the solvent from isooctane to normal octane, etc., you can change the aspect ratio from 4:1 to 6:1. So you can modify the aspect ratio of these rods. You can, this is in another system, you can see very smooth rods, very thin rods, and these are very broad rods by changing just the solvent. Here we have changed the surfactant. If you change the surfactant also, you can change the shape. You see they have become nearly spherical. It is the same material. If you take the composition, the material has not gone any change, only the shape has changed. And this change in shape you can control by using different surfactants. This is again another case. You can go from a rod, same material, you can go from a rod to a particle to a cuboidal system. This has dimensions of around 40 nanometers in this direction and maybe around 70 nanometers in this direction. Okay? And these particles are around 6 to 7 nanometers. These are very small particles. Of course, these are very smooth rods. This is again to show another role of another chemical. I didn't get into that. It's called a co-surfactant. If you modify the co-surfactant also, you can modify the width of the rod. Here you can see the aspect ratio is larger than this. Here the length and breadth are becoming nearly equal. Okay, so you can, so controlling the nanostructures can be done by this method easily. This is again by changing co-surfactant, you can go from longer, higher aspect ratio to smaller aspect ratio. So I will not go into this. Is more chemistry. Why does the aspect ratio change? That question. So that depends on what is called solvent bulkiness, the size of solvent. What is happening? The solvent is interpenetrating into the spherical geometry, and all these studies you can do by some dynamic methods like spectroscopy, etc. Okay. So this is similar things, so I will not go into that. Okay. This is again, if you change the water content, that means those spheres you are making, how much water is there. If you control the amount of water inside, which is called the W naught parameter, 11, 14, 16, you can change the size of the particles. Okay? So that also we have done, right? Okay. Now this is another type of rods. You can see the difference in the two rods. These are called single crystalline rods. You can see these rows. Each row is made up of a row of atoms. Okay? So, and it is very regular. That is why you see the these are called fringes. Okay? And but here you don't see that. So, it is called amorphous. So, we can control the crystallinity of the rods, and as you know, the crystallinity affects the properties of the material. For example, silicon, crystalline silicon is very different in properties, the band gap is different than amorphous silicon, right. So, all materials depending on the crystallinity, the properties will be different. So, we can control these things by doing certain changes. This is to show in more detail, this is an amorphous rod, and you can see that the particles are not ordered in a very particular fashion. So, this is a very high resolution picture to show how each particle is arranged with its neighbors. Okay. Now, I will come to some other aspects of nanostructures. These are silica. Silica is again a very important material. Silicon is important, silica is important. So, by different routes, we could make you can see very uniform silica particles. Okay. This is commercially available nano silica from a multinational company, but you can see our particles are much better than this. And of course, by modifying the procedure, you can get a very different morphology of silica. This is like spindle like silica, etc. Then what we do, this is some work we are doing to put the silica particles on a nano rod. Okay. So, what we do is we make the silica particles and functionalize it. That means, on top we coat with something which can react to something else, so it can bind. So, here we have coated with amino acids. Okay. Amino acids, as you know, is the basic building block of proteins. So, it has connection with biology or life sciences, right. So, you have these silica nanoparticles coated with amino acids, and those particles are then put on the nano rods, which we have shown earlier. So, now we have a system of nanorods on which you have silica particles which are coated with amino acids. So, our next game is to attach or see how these amino acids, because you know two amino acids bind to each other to form a peptide chain like to make a protein. So, can we, if you can bind this amino acid to another amino acid of a neighboring rod, then you can bring the two rods together. Okay. So, that is going on. This is another aspect of nanometals or nanoalloys, similar process of synthesis using microemulsions, and I will not bore you. These are type of nanoparticles you get. You can get pure copper, you can get pure nickel, you can vary the ratio 1:3, and you can, this is a high resolution picture to show that the particles are very, very small. Maybe this is 2 nanometers. So, this particle may be around dimensions of some 5 nanometer dimension. Okay. And this you can vary the composition easily, and by varying copper nickel ratio, you can vary the properties of these materials. Okay. I am not sure. Then you can also make in copper cobalt, you can make copper and cobalt one over the other. This kind what we call a core shell structure. You have a core of one metal, on top you have another metal, and this is of the order of maybe 80 90 nanometers, this is large. However, if you change the procedure, you will get copper and cobalt separate particles growing on each other. Here it is one particle growing on top of another, But here you have like a composite, both particles are growing together. Okay. So this is what I was telling is the core shell structure, and this has a lot of importance in many applications, because you can have a core which is magnetic, you can have a shell which has optical interests. So you can have two functionalities in the same particle. Okay. So these are some other examples of core shell structures. You can see the contrast in the high resolution TEM. So you may have one particle and then another particle, and depends on what is your aim, you can choose different type of core shell type of structures. Okay. Right. This is a very important material. Cobalt oxide is a magnetic material, and we have covered it with silica because we want to functionalize the silica for some purpose. Right. So let me come last 5. I have 5 minutes. 10. How much time? 5-10 minutes. Okay. I will talk a little bit about dielectric nanoparticles because a lot of engineers are there. So as you know, dielectrics are very important, and barium titanate is a very important dielectric material for multi-layer ceramic capacitors. And this is a multi-layer ceramic capacitor where you have barium titanate and then you have got metal layers embedded inside. So if you take a cross section of this in a SEM, scanning electron microscope, this each layer is of the order of 0.9 micron. Now the game is to lower this thickness. Okay. So if you see that in devices, the current feature size, this current means this was 2007 January, that was 140 nanometers, and the aim is to make it by 2014 50 to 70 nanometers. So how do you go about it? The way to go about it is either to work on the electrodes which are in between them, or work on the material which is the oxide material, or which is the dielectric, which is barium titanate is the well known dielectric, but you can have strontium titanate, other materials, right. So if you want to make thinner layers, you have to work with small particles. So nanoparticles or dielectric materials is very important, right. So miniaturization of MLCCs, you have to reduce the volume, and there are a lot of things you can do, but the cheapest thing that you can do is to reduce the size of the particles of the dielectric. But there are other things also you can do to miniaturize these MLCCs. Okay. So we have done a lot of work on making nanostructured dielectric oxides using microemulsions, which are also called reverse micelles. So we use a solution of barium, titanium, barium. We have developed some procedures by which we can get these nanoparticles. This is earlier I showed you 2 microemulsions, now you need to have 3 microemulsions because you have barium, titanium and oxygen. And so there is a protocol to be developed how you get these particles, and then you look at the TEM, etc. You prove it is nanoparticles, and like that we make host of other. These are all dielectric materials, and some of them are very single crystalline. Single crystalline means each particle is purely crystalline. It's ordered arrays you can see, and sometimes you get polycrystalline, sometimes you get single crystalline. Okay. And these are among the well-known dielectrics which are already used in industry. So we just made them in the nano dimensions. Okay. I don't know whether I want, I think I'll stop here. This is something to do with composites. I'll stop here. Thank you very much for your kind attention. This is my group at IIT Delhi.
I really enjoyed some of these, many of the images you showed, of course. One in particular with this, was it a carbon nanotube connected to 2 platinum electrodes?
Mm-hmm.
I forget which research group. I know it was part of the talk where you were giving it an overview.
I think the first slide or second slide.
I'm
Carbon nanotube connected to 2 electrodes.
Yes.
Maybe gold electrodes, is it?
Particular one I,
Platinum? I forgot.
well, I was remembering was platinum. But you didn't show the electronic
No.
signature. Have people, so I know people
People
tried
have
to do these
studied
measurements.
all those things, yeah.
Okay.
People have studied. That particular thing which I showed, they have done all the electronics.
All right, but it's, you didn't
The
go-
IV characteristics, etc., they have all done on that system. But I didn't go into that.
Okay. Thank you.
Thank you for your talk, sir. So I have two questions. One is that when you go from nanometer to micrometer dimension,
From nano to micron, or micron to nano.
Nano to microns.
Okay.
So how do you take care of the tunneling effect or the quantum effect which should be there, you know?
Quantum effects, as you know, is seen in nanometer dimensions, because for quantum effects, you have a size, you know, so you won't see those effects if you go to micrometer
The
dimension.
micrometer. And so how do you test it?
How do you
Like,
test?
yes, sir. Like when you're mixing different microemulsions together, or how do you decide on it? Or is it in a simulator kind of thing where you check?
Decide on the solutions, or what?
When you mix two microemulsions,
How do you find out what is happening?
yes, sir.
Okay, when you actually you get the particles, and then you have to do a lot of experiments, X-ray scattering to find the structure, then microscopy to look at the size of the particles, then you may do AFM, STM. If you want to do, if it is a metal particle, then you can do STM, measure the tunneling, etc. If it is a non-metallic, then you have to do AFM, okay, if it is a semiconducting or something, to look at the morphology and particles, etc. Then if you want to do properties, then you have to do, for example, you are interested in electronics, then you will do IV characteristics, okay, you will try to make a device and see whether it has a transistor-like properties or something like that. But if you want interest in magnetism, then you will study the magnetic properties. So it's a whole synthesis is only the starting, and then the game begins.
Yes, sir.
Okay.
When you, so with these ceramic nanoparticles, as you decrease the size, what happens to the capacitance?
Capacitance.
I mean, naively, one might expect that it will
The,
just
the dielectric
change.
constant normally goes down, because dielectric constant is a bulk property. So the dipoles, the larger the dipoles organized, you get a higher dielectric constant. So when you are making the particle very small, the particle has very little volume. It is more or less on the surface, and things on the surface have high surface energy, so they are more disordered. And when things are disordered, they will not give you a large moment or a large polarization, which gives capacitance. So ideally, when you go down to small size, you lose the dielectric constant, it decreases, but you gain many things. For example, energy losses are reduced, bias voltage required is less, things for, I am talking of MLCCs.
So are there any advantages to kind of choosing the kind of shape? So a lot of the particles you were showing had quite interesting shapes and sizes and
Yes,
so
yes.
forth. So can you choose a nanoparticle which has a particular shape which gives you an advantage in the dielectric?
In dielectric properties, shape, I don't think I have done that. Whether it is, if I can get a triangular particle, for example, there are some particles you can grow as triangles, but normally you can grow as rods or cuboids or spheres. These are the common structures, but I don't know whether, I have not looked at it on the shape versus the dielectric constant, but I have looked at the size dependence, yes, but not the shape.
I was just wondering that how you ensure the homogeneity of the preparation. Like suppose if you have to apply these nanoparticles for some application, because just the surfactant concentration regulation would suffice the homogeneity
The homogeneity
of the
it is
nano, yeah.
of the nanoparticle, that
Yeah,
you check using X-rays. Once you get the particles,
Now, you can only check the X-rays, but if you want to produce in the bulk amounts, how you will ensure that you are getting the homogeneity in the size or homogeneity in the structures?
that's what. For
What
structure, you have to do X-ray, and for size, you can do many things. You can do light scattering, you can do TEM, Okay, that shows you the size. And if you want to do the structure, if you have two structures, for example, it will show up in the X-ray.
I think she's asking not how do you diagnose the uniformity, but how do you
choose probably.
How do you make sure that it's uniform? I'm worrying about these capacitors having gaps and a breakdown because there's a missing nanoparticle.
Yeah, because you know in the normal,
I didn't get you. Yeah,
like I'll give you an example. When we do the normal phospholipid vesicles or along with the surfactants, we make sure that the size of the preparation is homogeneous by filtering to 0.2 micron, 0.1 micron.
No, this is a solution.
So, no, that's also a suspension. But
This is not a suspension, that's what I'm saying. A suspension is different from a solution. There is nothing suspended. When you make a microemulsion of this kind, it is a solution. So, it is homogeneously mixed at atomic level. That is, it is a solution, not a suspension.
Okay.
So, you don't have to filter through anything.
Thank you.